So, this short talk is about Redis. I read a book about it, Redis in Action. I liked the majority of it, and this talk is my takeaways from that book. So, I used to think of Redis as basically as a cache. In most architecture diagrams, you see Redis appearing in the role of a cache. And in the role of a cache, Redis is fairly simple, I'd say. So in this picture you see a client that requests some piece of data from a server, and that server could talk to a Postgres database on the right, but it could also use Redis as a cache to check if the data that the client wants is available in the cache. And if so, it returns it, and the server then forwards that back to the client. If Redis doesn't have that data, we have to go to Postgres, request the data, and return that to the client. And of course, if we do have that data, we might as well put it in Redis cache as well. So why does Redis shine in this setup? Redis is an in-memory key value store, and mainly that in-memory makes it really fast. And the key value store here helps as well, because if you're caching, you're typically having a value associated with the key. The key could be a primary key of some entity in the database, for example. So if you try to fetch that, you might as well query Redis with the same primary key and get the right result. Or you could even use the whole query string as a key, and the value would be the value returned from the database. And for that, you could store the value serialized as a byte array, for example. And because it is in memory, that has a couple of consequences. Like I said, it's very fast. It's much faster than having to read from disk, for example. If you already have that value in memory, it's very fast. But it has some downsides as well, because if the Redis server, for example, needs to reboot for some reason, or it crashes, the memory is cleared and all your data, all your precious data is gone. And if that is true, then Redis can only be used as a cache. You cannot rely on Redis for anything, basically, because if Redis dies, Postgres, fortunately in this scenario, has all the data available. So it would be faster if Redis was there, but it works without Redis nonetheless. But if Redis would be the primary source of data and it would restart, that data would be gone. So it would seem that Redis is only very good at scenarios like this for caching. But this is not the case, as I learned in the book, because Redis offers persistence as well. And it does so in two different ways. For example, it could write every command that you send to your Redis server to your database, to the hard disk as well. So if Redis then stops, reboots, starts up again, what it could do is replay all those commands to rebuild what it previously had in memory. And if you can imagine, that is quite slow. So if you're starting up such a Redis service, it's quite slow because it basically has to replay its entire history. And there are tricks with compaction to make that faster, but overall this is the slower option, I'd say. There's another option, and it's much faster, and that is to flush the entire contents of the memory to disk periodically. And as you can imagine, it's quite fast to load back. You just have to take what's on the hard disk and load that into memory, and you're good to go. But the periodically part makes this less reliant, because if I, for example, flush the memory every 5 minutes, then everything that happened during the last 5 minutes since the time that I last flushed to disk, all that data is gone. Because the data is only stored once every 5 minutes. That being said, this is really truly the faster option, not only for loading, but also for storing, because Redis has a nice trick where it kind of is able to fork its main memory, and the fork is written to disk, and Redis is able to process changes on the original. So flushing to disk is a non-blocking operation. So this is quite fast overall, both on the write side and on the read side. There's also a hybrid model where you flush to disk periodically, like before, but everything that happens after your flush is written to the event log. So you remember all the commands that were executed since your last flush. And then when you try to load back up, of course, first you load the snapshot, what's on the disk, into memory, and that could be, in the previous example, 5 minutes old. And then you replay all the commands from those last 5 minutes. So as you can imagine, the last 5 minutes is a tiny portion of the entire history, so that should be relatively fast. And I think this is also the recommended model to do persistence. But it's nice that you have an option between very reliable and very fast, but less reliable. So I think Redis actually has a pretty good persistence story. You can also run Redis in a cluster. For example, you can have a leader-follower model where every part of the data that is written to the leader is replicated to each followers. So in this case, the leader will accept all the writes, and that leader will make sure that every write is replicated to both followers in this picture. But every follower can be used to read data. And of course, that data might be slightly out of date because a write may not have been written from the leader and then to the follower yet. But it's an easy way to scale up at least the read side of your Redis database. There's a second way in which you basically have multiple leaders, and each leader is responsible for only a portion of the keys and the values that you store in Redis. So for example, you have 3 shards here, as they're called, and the first shard is responsible for all the keys that start with the letter A to I, and the second one is responsible for everything from J to R. And all these different shards will be able to accept reads and writes for their specific piece of the data. So also, you could use Redis in a cluster and scale it out horizontally quite nicely. So it's also, combined with the persistence story, a pretty good database to run at scale. But there's one more thing that I learned from that book, and that's where I want to spend the rest of this short talk on. And that is what I learned about the data structures that Redis supports. In the book Designing Data-Intensive Applications, Martin Kleppmann mentions the following. It says, besides performance, another interesting area for in-memory databases is providing data models that are difficult to implement with disk-based indexes. Data models that perhaps allow you to access the data that you want even faster than you would normally be able to, even if the data was in memory. So you can really have the combination of in-memory and those data structures to really accelerate fetching data. So let's look at the data types, or a portion of the data types that Redis supports. You see a bunch of keys on the left and a bunch of values on the right, keys 1, 2, 3, and 4. And the values here could be a boolean, could be a string, an integer, a byte array, basically the primitives you would expect from a key value store. And Redis offers a bunch of nice commands to work with these primitives. For example, integers. You can increment a certain integer, in this case the integer that is found at key 003, and you can increment that value by 2. So that value will become 4 plus 2 is 6. Redis also has a bunch of commands to, for example, expire key value combinations. So in this case, we might want to expire the value at key 001 perhaps after 5 minutes or at a specified time. So these are the commands that are really well suited for the caching capabilities that Redis offers. But there is more. For example, Redis offers doubly linked lists. In this case, we have a doubly linked list, whiskers, paws, and tails. And the beauty of a doubly linked list is that it provides constant time insert on both ends of the list. So there are a bunch of useful commands that we could use. For example, I can push to the left, that's what the L is for, L push, the value ears. So you see I specify the key 001 and then the value I want to push to the left. There's a corresponding R push as well, of course. I can pop from the right in this case, and this command will return the value that is rightmost in the list and consume it at the same time. I can get a subset of this list returned to the client with L range, and what you notice is that the very first value that we pass to each command is always the key at which the Redis value is stored. But Redis offers more collections. It offers a full-fledged set in this case. What commands does this set have? Well, it's very similar to the sets you would have in your daily programming language like Java, Scala, any other language you might be used to. So it has an add command, of course. Perhaps I want to add the value 0 to the set that you can find at key 001. So again, you have to pass the Redis key. It can check for membership of a set. It can remove elements from a set. Basically everything that you would expect from set operations. And this is just a tiny subset of all the available commands for sets. And the same goes for the list on the previous slide. There are many commands at your disposal to manipulate these lists and these sets, perhaps even more than your current programming language offers. And what is also a nice mnemonic is that every command that operates on a set starts with the letter S for set. Redis offers hashes as well, so hash tables or maps or dictionaries or whatever you're used to calling them. So in this scenario, we have, I show it here as a table. We have a key name that is associated with the value Pookie. So it's the name of the cat you can see on the right. And as you can see, that cat is 6 years old. It's a male and its breed is Burmese. And this is a nice way. So the hash values allow you to store records in Redis values, which are much richer, of course, than just plain strings, or if you would have to decode your own records into a byte array and deserialize that afterwards again. So it's very convenient to store records in this format. So what commands can we use to manipulate hashes? We can get a value from a hash at a certain key. And notice that there are two keys here at play. So the first one is the Redis key, 001. And the value at that key is a hash. And we can get a value from that hash with the second key, which is name. So this command, hget, would return Pookie. I can put a value in a hash. I can delete a value from a hash. So again, nothing surprising. Things you are used to doing with dictionaries, maps, etc. I can also get all the elements, so basically the entire record, from a Redis hash. And this will return them as a sequence where the first and the third, every alternating odd value is a key, and every even value is an index. So in this case, it would be a sequence with first name, then Pookie, then age, then 6, etc., etc. And this sounds slightly inconvenient, and I think it is a little bit inconvenient, but most Redis clients will transform this to you back into a map or a dictionary that you're used to working with. So you don't really feel this downside in practice. And like the sets, all the commands for hashes will start with the letter H for hash. It has another very interesting data type, a data type that I have not seen before, and they call it a Z set, or also described as an ordered set. And the members of the set are the values on the left. So the members of the set are whiskers, paws, tails, and nose. Those are the members of the set, and they are associated with a floating point numeric value, and that's the one you see on the right. And in this way, my first instinct was this is not a set, it's another flavor of map. But now Redis insists it is indeed a set, and the keys of what I thought was a map are called the members, and the values are called the scores. Now, why does Redis insist on calling this a Z set, an ordered set? That is that it is indeed a set and it's ordered by those scores. So basically you pass a ordering floating point value along with every value you want to add to the set, and Redis will make sure that you can access that in sorted order. So what are commands for Z sets? Well, you can add a value. So the first parameter to Z add is 001, that's a key, and at a value we will find a Z set. And then there are two parameters. The first one is a score, 16.23, and the member of the set is the nose. So I've added a nose associated with 16.23. I can get a range out of this, and these are the indexes, 0 to 2. So what I can do is request the members, the first three members, 0, 1, and 2, from that Z set that is of course ordered by those scores. So in that way you can do basically top 5s of something, right? Or order something by a date. I can remove things as well. And there you see again that Z prefix that indicates that it's a command for Z sets. And I can also get ranges by the score, as I mentioned previously. And so the unique thing about these sets are not the scores. The unique values are the members. So you can have multiple members associated with the same score. And you can get, like I said, Z range by score. You can get ranges of values by score. And in that way, it's kind of like an index. It behaves much like an index in a relational database. And people actually use it like that as well. So what can we do with this? Well, the book describes in the very first chapter a nice little project that I want to re-implement for you in the next 3 to 4 slides. So really very simple. And it's a Redis clone, which is normally a pretty ambitious project in a relational database, especially if you want to be able to get high throughput. Well, because Redis has the right data structures for high throughput and it's all in memory, this very simple Redis clone is very fast nonetheless. And I think the author of the book Redis in Action reports being able to easily serve 100,000 requests per second for his very simple Redis connection. So what does a good Reddit article have? Just to summarize for you real quick. It has a title, at least in this implementation, it has a title. It has a number of votes. You can vote a article up or down, for example. It has a bunch of comments. It's posted by a certain user, in this case, Hooklove. And we're going to focus in this scenario on a Reddit clone that always sorts by post date. So you only get the newest ones at the top of your page. So we're going to ignore the votes for now, for a little while. Okay, so how will we model our Redis database for our Reddit clone? Well, we want to store articles, and as I mentioned, it's a good fit for a hash. So if you want to store a record of a certain kind, use a hash. So the title here is After a Long Day, and you saw from the previous slide it had been a really long day for that cat. It has 24 votes so far. It's posted at, and I've displayed it here as a numeric value, and that is on purpose, a floating point numeric value, so that should hint at something. 2021 0308, so that was posted yesterday, the 8th of March, and it's posted by a certain user. And as you can see from the way I created my key, it's prefixed by article colon, and Redis only has a single key space. So all the keys live in the same space, and that is quite inconvenient if you have different types of entities that want to inhabit that space. For example, a user and a post may have the same ID. So how do we prevent that from conflicting? Well, in Redis, you would prefix the ID of the article, 123 in this case, with an article colon prefix. It's basically acts as a namespace or a table name, if you will. So this posted by, you can clearly see that it is another Redis key, user colon 003. And at that colon, at that key, you will probably find another record that describes the user. And in this way, you can prevent user 003 from conflicting with article 003 because they have a different prefix. So how do we know that the current ID is 123? Well, we'd like a sequence. That's what we would like. And Redis has your back. Because, so here we have the ID namespace. So it contains perhaps IDs for certain entities. And the entity in this case is the article. So at this key, we find a integer, which is the next ID in line. And we can use that handy increment command to constantly increment. And the nice thing about that increment is that it returns the value that it found at that key. So you both get an idea and you increment it at the same time. So much like a sequence in a database. In a relational database, because Redis is a database as well, right? We want articles to be sorted by time. So I put it at a sorted colon time key. And in that at that place, at that key, we find a value that's a Z set. And you can find as members all the IDs of the articles that we posted, and their score is that floating point posted at timestamp. And so the sorted time Z set is the article IDs sorted by time. So you will find at the beginning you will find the oldest articles, and at the end you will find the newest articles. And then finally, for tracking votes, you cannot see it because my head is on top of it, but we have a set here that contains the user IDs of the users that have voted for a certain article, and the article votes are stored at a key voted colon and then the article ID, which also includes a colon. So you can sort of create nicely nested a tree-like structure for your keys. So although it may seem limiting to have only a single key space, Reddit users manage just fine. So how do we manipulate this database? How can we create articles, vote for articles, and grab, for example, the top 10 articles, the top 10 newest articles? Well, I've created this imaginary weakly typed programming language. You will see it here in black. So I want to create an article. It's a function, and all we need is a title and a user ID. And the first thing I do is I grab the current time, because I have to store that in two places. In the article record and also in the ordered Z set that we use to sort article IDs. Then the article ID, so the next in line, is whatever ID we find at ID article, and we increment it at the same time so that we get a continuously increasing range of IDs. And this one is a Redis command. So I'm basically mixing this language and Redis commands. But I think for these simple examples, it works well enough. The article key then is that ID prefixed with article colon, which is the namespace, as I explained. Then we want to create a hash and populate it with a bunch of values. And the nice thing about HMSet is that we can pass it multiple keys and multiple values, like we get it from hgetAll. You have to alternate the keys and the values. So here I say I want to set at the article key, I want to create a hash that has these 4 keys and the associated values. So the title is the title. It gets immediately 1 vote because the user that creates the post is likely to vote on it. It's posted at a current time and it's posted by the current user. And then of course, and this is a Redis command, and then of course we have to add it to our zset as well. Again, a Redis command. So at the sorted time key, we insert the article key with the score that is the time. So that is how we create articles. Really easy, and it's nice to know that this performs really well, even for such a simple thing. Of course, we can vote for articles. All we need is an article ID and a user ID. Who is voting for what article? We construct the voted key, which is prefixing the article ID with the voted : namespace. And we try to add the user to that set of users that have already voted on the key, on the article. And if we succeed, if that user is not already in the set, then sadd, which is a Redis command, will return a positive value. So it says, yes, I have successfully added this user to this set of users. And if it returns a negative result, that means that that user was already in the set, was already a member of the set, and that means that the user just tried to vote multiple times for the same article. So we're not going to do anything in that case. We're only going to continue with whatever is in the if we just added a new user to the set. And in that case, we can safely increment the key votes in the record that is found at the key. It gets hard to talk about, but I think you can pretty well visualize this. So we increment the vote count in that record by 1. So it's even easier to vote for an article. So now, how do we get a bunch of articles? We need a page index and a page size. So which page are we looking at? Supporting pagination all at once in a small block of code. So the first 2 things that we have to do is determine what is the start index and what is the end index. So, and you can see that it's fraught with off by 1 errors, but I've managed to copy this from the book just fine. So this is the index of the articles that we want to return. Now we need to fetch the IDs of those articles, and we use it with zRevRange. And we use rev, of course. We don't want the range from 0 to 10 because those are at the beginning of the zset. Those are the old articles, and we'd like the new articles, please. So we get the range from the back of the zset. Page start and page end. So this should return those article IDs that we saw earlier, but article IDs are not articles themselves. So how do we transform those IDs into articles? Well, we map over the IDs and transform each ID into an article by just grabbing that from the database, from the Redis database. And of course, you can immediately feel that this is quite heavy-handed because we're going over the network multiple times. So we're going over the network for the zRevRange, and then again for each article in the page. So for example, if you have a page size of 10, then you will go from the server to the Redis database 11 times. And it could be much more efficient by batching all those hgetAll requests. And that's exactly one of the improvements that we could do. And it's also discussed in the book, but not in the first few chapters. So it will basically store all those commands and buffer it locally. And then as soon as you say, okay, I'm ready, I did all my commands, then it will go over the network once, execute all those commands, and return the results of those commands back to you. So it only would require you to go over the network twice. And another thing you may have noticed is that it's not quite, it doesn't feel quite safe. We're not in the context of a transaction, so we might easily get some dirty reads here. Redis does support transactions, but it's quite primitive. So if you, it's an optimistic locking model, and you have to do the locking yourself. So if you're about to read from a value in Redis, you basically execute another command that says, okay, I'm about to read it, lock it, and not in the pessimistic sense, but in the optimistic sense. And then whenever your transaction completes, the whole thing gets sent to Redis, and it's checked that whatever you read is still accurate, is still consistent. So you have to do a bit of work yourself to get those transactions. Now, a couple of more, but then functional improvements that we could make. One example is that instead of, I'm going back a lot now, instead of having a z-set sorted by time, we can have another z-set, and that one is not sorted by time, but sorted by relevance. And you could say that relevance, and it needs to be a floating point number again, could be initially, it could be the post time, but then every time someone upvotes this article, you could increment that value. So for example, you say that an article that is 1 hour old but has one upvote is about as relevant as one article that was created just now but has no upvotes. So in that way you can kind of get a true score of those articles by mixing both time and upvotes. So if a article stops getting a lot of upvotes, it slowly goes down in the list. So in that way we can support multiple sort orders by using different z-sets and different scoring mechanisms. But yeah, unfortunately I don't have time to go over all of the intricacies, but it's not too complicated. And one last thing, because this was my final slide, and one last thing that I wanted to mention is that, well, I've learned that Redis is a really cool database. It's capable of much more than just caching. It's really something you can use in a high performance situation, and the things you want to read often, or the things you want to be really fast, you could store that in Redis. And of course Redis is an in-memory database, and that would mean that everything that you want to read should fit into the memory of the machine you're running Redis on. And that's of course very limiting. So you cannot store everything in memory, but the couple of things that you do want to store in memory, you could access that really fast. So for example, we're not storing the comments in the Redis database here. We could store that separately in a Postgres database, for example. So the overview is really fast, but then if you want to load the comments, that takes a little bit longer because we use Postgres, has to read from disk, etc., etc. But in most cases, I think that's acceptable. And if that's not acceptable, you could even say, well, I'm going to just store the first page of comments, so the first 10 or 20 or so of those comments, I'm going to store that in Redis because I want to be able to serve that up real quick. And then in the background, load another bunch of pages from Postgres. So that way you can get a really fast response time, even though keeping the memory footprint of whatever you store in Redis low. So I kind of fell in love with Redis. I haven't used it for a real project yet, but I could definitely see the added advantage. I hope you've enjoyed this short talk, and yeah, I will take your questions now.